Hello everyone, welcome back to my channel. My name is Bin Ouyang. I'm a material scientist working in the field of computational material science and autonomous synthesis. This is my channel for sharing my understanding of material science. I will post either my comments of some recent papers, some mini tutorials about computational material science, as well as my daily life as a material scientist. Please subscribe if you are interested in those videos. I'm currently a postdoc working with Professor Gerber Cedar at the University of California, so I'd like to share some of my research experiences when I was working in the Cedar group. So in the last video, I have talked about predictive synthesis of ceramic materials. So this is the second half of that video. As in the last video, I was mainly focusing on talking about, like how do we engineer the precursors so that we can tune the structural phase transformation in a layered metal oxide. So this is the only way that we can do, this is one of the ways that we can do it, but we actually have a lot of other alternative synthetic pathways. So in this video, I'm going to focus on the last 3 papers. It's actually 4 papers that I did when I was doing my PhD at McGill University. All right, let's get started. So first, let's try to recap what I mentioned in the last video, the waterfall principle 1. So the waterfall principle 1 basically tells you that the chemical reaction is essentially a waterfall, right? So like a waterfall, gravity controls everything. In a chemical reaction, the thermal controls everything. So what you need to do is actually to find the best precursors that starting with a high chemical potential so that the thermodynamic driving force is going to push the reaction from the high energy state to the low energy state, right? So you just need to place your precursors in higher chemical potential compared with the target. This is not the only way that we can do it. So we actually have a waterfall principle 2. So we can just flip the waterfall. So we can flip the energy landscape so that, like the thermal still controls, but now the previous low energy state now becomes a high energy state thermodynamically. So even though you can start with some very stable precursors, but by flipping the synthesis space, you can still trigger the reaction among those precursors, and they're gonna finally still form the targeted materials. Thermodynamically and mathematically, this is called Legendre transformation. So in a solid state synthesis, the free energy of the system is defined as a function of composition and temperature. So this is easier to understand as what we do is just mix different fractions of compound. For instance, if I synthesize A to B, we're basically mixing 2 mole of A with 1 mole of B and heat it up. So we only need to take care of the ratio of the precursors as well as the temperature, right? But this is not the only way that we can do synthesize. We can, do a Legendre transformation. Mathematically, we can have a new free energy, which is a function of a ground potential. This can be the free energy at the reference composition temperature. But in addition to that, we actually add another term, which is another gain of free energies as a function of other synthesis conditions, which those conditions can cover, like pH, solvent, substrate, mechanical deformation, electric field, magnetic field, etc. So there's so many handles that we can play with in experiment. So this is how Legendre transformation is gonna work. So the next topic is basically, like how to replace the typical solid state mix and heating up process to some kind of a novel synthesis process. So let me give you one example. Like in the field of 2D materials, we have the famous materials molybdisulfide. It's actually a lubricant materials if you are working in the industry that is relevant to frictions and the lubricant. Like molybdisulfide is also a ceramic materials, typically in the industry, what we do is just to mix molten metal with the sulfur and just heat it up to like a few hundred degrees C, and the 2H phase of molten disulfide gonna form. So if you look at the phase diagram, it's actually calibrated from experimental data. It basically tells you that you can only form 2H molten disulfide regardless of the ratios of the precursors as well as the temperature of heating up. So these materials actually have several polymorphs, which we call them 1T, 1T prime, and 1T double prime phases. They have very different structural crystalline structures, and they have a very different electronic structures as well. Like 2H phase is a semiconductor with a band gap around 1.8 electron volt, while 1T is a very good electrochemical catalysis, and for hydrogen evolution, for instance. And the 1T prime is actually a 2D topological insulator. So there are some fancy and fantastic physical properties for us to study. So in order to synthesize the 1T prime and the 1T double prime, as well as the 1T phase, we cannot just heat it up by mixing different precursors, right? And so what is the alternative synthesis pathways to it? In my PhD thesis, I actually developed four types of synthesis conditions. And we can also blend some of the synthesis conditions to create new synthetic pathways. So these conditions are either electrostatic gating, tensile strength, interfacial charge transfer, and curvature. So if I couple electrostatic gating and tensile strength, I have demonstrated in this phase diagram that the phase transition can be flexibly tuned around when you play with the coupled elastic strength and electrostatic gating. And if you want to couple the tensile strength with the interfacial charge transfer, you're basically designing 2D heterostructures by by making an adhesion between this molten disulfide monolayer with a silicon monolayer. So in that case, we can also tune the phase transition. And if you only want to use the interfacial charge transfer, you can design an epitaxy growth. So it's basically a substrate engineered. In this work, we actually demonstrate that by using different metal substrates, you can also effectively tune the phase transition of these 2D MX2 materials. And the last thing is about curvature, since we're dealing with ultra thin film, since they are 2D materials. And one common things you can find in these materials is they are never really flat. There's always different kind of buckling and rippling in those materials. So we should also take use of them by create different kind of curvatures in these 2D membranes. And with the existence of the curvatures, the phase transition will also be triggered. So all those work are actually published in 4 papers, which dating back to my PhD thesis. So please feel free to look at more details in the paper. So let me give you a little bit more information about how exactly it happens, since actually 2 of these 4 state variables are related to mechanical deformation, right? So let me tell you the concept about mechanical metallurgy. So this is not really like a very new concept, even though like recently a lot of people start to talking about it. Mechanical metallurgy, coming from the industry of metallurgy actually, it refers to the triggering of phase transition by doing mechanical deformation. So this actually gives us a hint that can we actually do some kind of mechanical deformation to ceramic materials, even though mechanical metallurgy are typically used in the field of metals and alloys because they are super plastic. So the mechanical deformation is going to work. So how about ceramic materials? Ceramic materials is not always easy to be mechanically engineered. So I will give you one example. Like in 2014, there's a Nature Com paper published by Professor Evan Reed in Stanford University. And for DFT calculations, they demonstrate that if you stretch the molybdisulfide materials with a tensile strength of 20%, you're going to actually trigger the phase transition. So however, this looks like interesting, but if you do any tensile testing in the real materials, you're going to realize the elastic limit of these materials is up to 6% to 11%. So which means before the phase transition going to happen, the tensile strength will break the materials first. So these predictions unfortunately become unrealistic for a real experimental design. So this actually inspired me of thinking about, like how about we create some kind of a collaboration between different state variables, right? So how about if we couple the strength with electrostatic gating? So this is a phase diagram. I didn't show the number here yet, but from the trend of different colors, so the purple are basically the 2H phase, while the yellow and the blue are different 1T prime and the 1T double prime phase. So you can clearly see that if you have no electron density, you need a very large strand, right? But the curvature actually goes up, which indicating that when you have electron density, the critical strand you need is going to be hugely decreased. I'm going to show you the real data and some detailed analysis in the next slides. So this is one way we can do it, is to do some kind of electrostatic gating by adding more electrons into the materials and stretch it. So the second thing we can do it is actually to do a heterostructure. So the electron can also come in from the other part of the interfaces. So here in this phase diagram, I demonstrate that by forming the molybdisulfide heterostructure with a silicon, which is another 2D materials, you actually only need less than 10% of biaxial strand, which is actually 7 point something percent, and the phase transition will already be happen. And keep in mind, 7% is actually within the elastic limit. It's actually like more than half of, it's actually less than half of the biaxial strand that is predicted in this paper. So in that case, we have two more experimentally achievable way for achieving the phase transition. All right, a little bit more analysis on why this is going to happen. So if you look at the energy landscape, we can plot the free energy of the materials, the 2H, the 1T prime, and the 1T double prime, as a function of strand. But now we actually have charge density. So basically these materials are charged with 0.1 Q0. So this is actually means every formula unit of molybdisulfide, there will be 0.1 electrons injected. So in other words, the moly is likely to be reduced by 0.1 charge state. So this is not something that we cannot do in experiment, right? So it sounds like really feasible. And with this small amount of charge injection, we realize that, if you draw a tangent line from this free energy, they're basically gonna tell you the solubility limit of these two phases, right? So in that case, the 2H phase will start to make phase transition to the 1T prime phase. It's actually 1T double prime phase here, at a strength up to only like 9.5%. And if you keep increasing the strand, the phase transition will finally finish when you reach 14% of the strand. So in other words, with such amount of electron injections, the phase transition will happen if you have more than 40% of strand on the membrane. So in that case, what we can do is actually to design a device, because like 2D materials are always designed to be transistors. And by designing such kind of 2D transistors, we just need to add a gate, and then we play a gate voltage so that the Fermi energy is going to be raised up, and the electrons going to be injected into the membrane. So as a consequence of that, the phase transition can be happen. And you can also switch the phase transition by switch the gate voltages. So this is not some kind of imagination from DFT calculations. It's kind of interesting, like after 2 years, a collaboration work between UC Berkeley and Stanford actually experimentally achieved, like the first gate-induced phase transition is such kind of 2D transition metal dichogonized materials. So that is actually a proof of the feasibility of my computational prediction. So what else can we do by just stretching the materials? We know like we cannot always stretch the materials, right? So the first thing we can do is actually to create a ripple on those materials. You know, like the 2D materials are never as flat as we think. There is always different kind of small curvatures in the membrane when we grow it by doing either like CVD or MBE. So in that case, I construct this phase diagram which describes the energy landscape as a function of curvatures. So when we define a curvature, we can define two principal axes of rippling, right? So if we only have curvature in one rippling directions, we're creating like a ripple. So there will be only curvature in one direction. And at the same time, if you have curvature from two perpendicular directions, it's going to be a buckling, right? So they're going to create a bubble in these membranes. So this phase diagram can actually tell you both how does the rippling and how does the bubbling going to influences the phase transitions. So in the real experimental design, you know, the rippling can be induced by simply compress the membrane, right? So if you want to compress like a paper, the paper will not really be compressed, right? Instead, they're going to be ripples of the papers, since this is the way that they can release the energies, especially like the strain energies introduced. So at the same time, to create a bubbling, what you can do is actually to do a nano indentation to the membrane, right? So actually at the same time, they publish in 2 different years, but actually the submission of these 2 papers is actually at the same year. So the first paper is published by me, while the second paper in Letter is actually published by Professor David Sorowitz at the University of Pennsylvania. And in that paper, they actually did larger scale simulations using finite elements. And they come up with the same conclusion that if you introduce buckling of the materials by doing this nano indentation, you can actually effectively tune the nucleation and phase transformation of the 1T prime phase in the 2H membrane. So that is actually evidences from both microscopic and macroscopic that the phase transition is going to happen if you create a curvature. Okay, so if you are working in the field of, like if you are doing typical solid state synthesis, and if you are working with like powders, you may not be so impressed, right? Because curvature can never be achieved in powders. And it's also difficult to really like stretch particles, right? We don't have the device designed for that. So here, another alternative way is to create a shell deformation. So that is actually achievable in particles or like powders. So the way to introduce a shell deformation in those materials is actually to do ball milling or like shake milling. So what happened in the ball milling process and shake milling process is actually they can create actually a very large shell deformation to the particles because they are turning the particles away from 2 different directions, right? So from computation, this is actually a work from my colleague Tang and Peng Hao in Theta Group. And they have demonstrated computationally that, by creating shell deformation, the phase transformation, in other words, is actually the activation barrier in the very beginning is very large, but with enough shell deformation up to like 2 gigaparts, the phase transition will automatically happen without even any activation barrier. So that actually explains the ball milling phase transformation from the beta sodium iron oxide to the actually dissolved rock salt alpha sodium iron oxide. So experimental results is demonstrated on the right side. The XRD basically tells you that there is indeed a phase transformation if you do this ball milling synthesis. So that is the evidence that, like by just mixing and heating it up is not the only solution when we synthesize the ceramics. Sometimes ball milling conditions can actually create a mechanical deformation to the particles so that the phase transition will also happen because of the remnant stabilities under the mechanical deformation. So that's pretty much about the concept of mechanical metallurgy. So in the end, I'd like also to talk about the epitaxial growth. This is a huge topic in the field of thin film. And I believe a lot of people are working in the field of thin film, like people are doing either multiferrotic thin films. This is a very hot topic in the field of oxide, especially transition metal oxides. And also, if you're working on 2D materials, you're likely to grow in different thin films and nanofilms using either chemical vapor deposition or physical vapor deposition or molecular beam epitaxy. So the epitaxial growth is actually also like a well-explored experimental synthesis approach, right? So here in this paper, I showed that I did a high-throughput computation on different growing substrate, which typically we use metal as the growing substrate of 2D materials. And it has been shown by the DFT calculation that whether there will be a phase transition in this 2D metal dichogonized is really depending on whether you have the right metal substrate. So in this figure, all the field symbols are basically the metal that can trigger a phase transition, but all the open circles are the metal that will not trigger the phase transformation. And the mechanism behind such behavior can be described by a charge transfer from the metal to the MX2, which is the transition metal dichogonized. So from DFT analysis on the beta charge transformation, we realize that the more the phase transformation happens from the metal substrate to the transition metal dichogonized, the more chance you're going to have phase transformation. So if you look at all the field symbols for 5 types of transition metal dichogonized, you're going to realize the maximum phase charge transfer from the 2H to the 1D prime will always actually favors 1D prime phase, because which can be shown by these field symbols in this 5 subplot from figure A to figure D. So, and the reason behind it, and the reason why different metals have different roles here is because they have different, like work functions. In other words, they have a different affinity to electrons. So if you are working in the metals that prefers to donate the electrons to the transition metal dichogonized, the phase transformation will very likely to happen because you feel some sort of like ionic like charge transfers. So in other words, like the metal dichogonized is gonna get extra charge from the interfaces between the metal and the transition metal dichogonized. So that is actually key for phase transitions. And that also explains why some ionic metals such as scandium, chromium, niobium, vanadium gonna work the best in terms of all sort of transition metals. All right, that is the end of my presentation and my story of the synthesis science. Please let me know if you have any questions and comments. So I will see you in my next video.